Hello and welcome to the frontiers of parameterized complexity. Our guest today is Jason Lee, who will be speaking on a new and fast algorithm for feedback vertex set. Please, Jason.
Can you hear me? Okay.
Yep.
Okay. So I'm from CMU, and this is joint work with Jesper Nenadolf, who's currently at Utrecht University in the Netherlands. Okay. So let's begin with the problem for this talk, which is the feedback vertex set problem, which is given a graph, you want to delete the you're given a graph, you want to delete a set f of vertices such that G minus f is a forest. So equivalently, that means that you want to find a set f of vertices that hits all the cycles of G. And in the parameterized complexity setting, we're given an additional parameter k, and you want to find a feedback vertex set of size k, or determine that none exist. Okay. And in the parameterized complexity setting, we typically want algorithm that has feedback fixed parameter tractable in k, which means it runs in time some function of k times a polynomial factor, where the exponent in the polynomial factor does not depend on k. And typically, in this setting, our goal is to minimize the function f of k, whereas the polynomial factor doesn't matter in this setting. So typically, you think of f of k as like some small exponential in k, and we want to minimize this base exponent. Okay, so this problem has seen a lot of work in the past. Some most notable results are the first FET algorithm for this problem was due to Downey and Fellows from '92, and then Becker et al. gave a very nice randomized algorithm based on random sampling that gives us f of k equals 4 to the k. So at this point, this exponent is already a single exponential. But of course, there's still action on is 4 the right base exponent. And turns out this can be improved. In 2011, Cygan et al. Gave a randomized algorithm that was 3 to the k based on this now well-known cut-and-count method. Their algorithm actually runs in time 3 to the Treewidth with the graph. In this talk, we won't go over formally what Treewidth means, but it's a parameter that allows us to do dynamic programming on the graph and is very well suited for FET algorithms. And now it is well known that if a graph has Treewidth at most k, if the graph has a feedback vertex at most k, that has a Treewidth at most like k plus 1. So in which case we can replace Treewidth by k. But actually in this talk, we'll actually need the fact that it runs through the Treewidth time to obtain our improvement. So we should keep that in mind, that this algorithm actually runs in time 3 to the Treewidth. In 2014, Kokiomaka and Pilovchuk showed that proved the best deterministic algorithm known so far, which runs in 3.62 to the k. And this is where our result comes into play. So after about 9 years, we provide the first improvement in the randomized complexity, and we showed that f of k is actually at most 2.7 to the k. So the improvement between 2.7 and 3 is not. You should think of this as like a message that a conceptual message that the barrier 3 to the k can be broken. The tools we use are kind of complex, and more or less our goal was just to break this 3 to the k barrier. Whether we got 2.7 to the k or like 2.999 to the k was not qualitatively that very significant. The point is we can break through the 3 to the k, and hopefully that kind of revives this race to get the best running, that kind of shows that improvements can be made and kind of revives the race on how to get the best base exponent, which hopefully leads to like further ideas that can be used in more problems in parameterized complexity. So our main techniques is we combine ideas from this random sampling algorithm due to Becker et al. And the cut-and-count method due to Cygan et al. So keep in mind again the fact that the cut-and-count algorithm actually runs in time 3 to Treewidth. We'll be using that later on. So any questions so far? Okay. So for this talk, we'll just be focused on getting like a 2.999 to the k algorithm, or just how to break 3 to the k. Getting 2.7 to the k requires more technical details that I won't have time to go over in this talk. But hopefully, the goal of this talk would be hopefully to give like a more or less self-contained algorithm to beat 3 to the k, and see what are the techniques we use to break this 3 to the k barrier. So this epsilon will be very small, but again, it's the goal is to like establish a conceptual message that we can beat 3 to the k. So a popular technique in parameterized complexity is the notion of reduction rules, which are these polynomial time operations that we can take on the input to make it smaller while preserving the solution structure of the graph, solution structure of the input. So for example, in Feedback Vertex Set, where we're given a graph G and an integer k, the parameter k, a reduction rule corresponds to transforming G comma k to some G prime comma k prime, where preservation means that we want the property that if G has a size k Feedback Vertex set, then so does G prime. And typically, well, why is it called reduction rule? Is there a question? No. Oh, that is true. That is true. Good question. Right. So this is where we'll actually need the technique of iterative compression to give us this Feedback Vertex set of size k, or k plus 1 actually. So you should keep that in mind, that we do need this FES for size k, but it can be given to us for free. So going back, why is it called a reduction rule? That's because typically we can think of either when we do this transformation, typically either G prime is smaller than G, or K prime is smaller than K, so we can make progress in a sense. So that's why it's called a reduction rule. But the formal definition does not require any relation between G and G prime. So what are some common reduction rules, folklore common reduction rules for the Feedback Vertex set? One is, well, suppose the graph has a self loop at V. So we call this graph can be a multi-graph. That's allowed. And suppose a V has a self loop. Well, that means again. So here it's more useful to think of Feedback Vertex set as hitting all the cycles of G, where we have a cycle, we have a self loop, a single vertex as part of a cycle. So you must hit V. So you must select V in the Feedback Vertex set. So here's a very simple reduction rule. We go from G comma K to G minus C comma K minus 1. So why does that work? Because well, V has to be in the Feedback Vertex set. So it suffices to just greedily select V and then solve on the remaining graph, where now we only have K minus 1 vertices remaining. Okay. So you can see, so like more colloquially, what we're doing is we're just removing V and decreasing K by 1. So that is our reduction rule in more colloquial terms. So second reduction rule is, suppose G has a leaf vertex, a vertex of degree 1. In this case, I claim that V cannot belong to any cycle, because if V belongs to a cycle, it must have degree at least 2. Yeah, it has one neighbor from each direction of the cycle. So this is, we can just greedily remove V, and do not add it into the Feedback Vertex set. So we just remove V and go from G comma K to G minus C comma K. But lastly, the third classical reduction rule for FES is, suppose V has degree 2. Then in this case, so again, at this point, it's also more useful to think of FES as hitting all the cycles. Now, any cycle hitting V, any cycle including V, must also include U and W as well, because V has degree 2. So it must go enter from either U and V and exit from either, enter from U and or W and exit from either U or W. In particular, any feedback vertex set that contains V must also contain U. So if we select V in the feedback vertex set, we might as well also select U instead, because U will hit at just as many cycles as V will, and possibly more. So in this case, we can just imagine ignoring V, because we might as well select U later on if we need to. So what we're doing is we're deleting V and we're adding the edge U, W. So essentially we're unsubdividing the edge U, W. So you think these guys like reverse subdivision. Okay, so these are the three well-known reduction rules for feedback vertex set. And what it gives us is, it gives us a graph. Once these rules no longer apply, it gives us a graph where there are no self loops and the minimum 3 is at least 3. So again, so these properties will be important later on in establishing our algorithm, and we can more or less obtain these for free, right? Because all these rules are polynomial time, and they're all sound in a sense. They're all preserve the solution structure. So for the rest of the talk, we'll assume that the graph has no self loops and has min degree at least 3. So let's first, before we proceed with our algorithm, let's first go over the Becker algorithm reduction, which gives us this 4 to the k running time. And we'll again, our algorithm will improve upon theirs. We'll build upon theirs. So so let's first quickly go over intuitively how Becquerel's reduction works, and intuitively why it gives us a 4 to k algorithm. So for their algorithm, it's more convenient to think of their algorithm as doing a probabilistic reduction, which is going from G comma K to G prime comma K prime, where this reduction can only succeed with some probability P. Think of P as like a constant. And if it succeeds with probability P, then we have the property that if G has a size K FES, then G prime also has a size K prime FES. Now here, we typically want K prime to decrease by at least 1, because this only succeeds with some small probability. So we want to make enough progress such that we don't have to do this too many times. And these probabilities will like multiply up to get our final success probability. Okay. So Becquerel's algorithm is very simple. So again, assume that the graph has no self loops and min degree 3. Then what they do is they simply sample a vertex V proportional to the degree of V. And they show that, and then they greedily add V to the FES. So they have this reduction rule from G comma K to G minus 1, G minus V comma K minus 1. And they show that if G has min degree 3, which is our assumption, and the instance has a solution, so G has the FES of size K, then with probably at least 1/4, V is in the FES. So in other words, this is a probabilistic reduction. By sampling a random vertex V proportional to its degree, this is a probabilistic reduction that succeeds with probably at least 1/4. Right. So again, so what does the algorithm look like? Basically, it would first apply the reduction rules 1 to 3 we saw before until G has min degree at least 3. And then at that point, it will sample a random vertex V proportional to its degree. And then apply this probabilistic reduction, which succeeds with probably 1/4, but decreases K by 1, which is very important. That means they can only this reduction can only be done at most K times. After that, G minus V might still we might still be able to do reduction rules, the first 3 reduction rules on G minus V now, because you might create leaf net vertices, for example. So we do that until we cannot anymore, and then we apply this reduction rule again. And can just repeat these 2 processes until K is 0. And the point is, we can apply this probabilistic reduction at most K times, because every time we do it, we decrease K by 1. So therefore, we get a 4 to K algorithm. So now you can ask, what was 1/4? So naturally, to improve this forward to decay running time, we want to improve the probability that we get a vertex in the FES. Well, turns out this 1/4 is tight in the following case. So imagine just K is 1, a graph where we want to find a single vertex that hits all cycles, or whose removal makes the graph acyclic. And the graph is just take a path graph and just add one single vertex, connect to everyone. Now you need to add 2 parallel edges to each of the endpoints to force a degree to be 3 everywhere on the path. And the point is, in this graph, there's only one size 1 FES, which is just this vertex. And this vertex has degree roughly n, because there are n-1 vertices on this path, and each of them has around one edge to this vertex. So degree is roughly n, but a total degree is n plus n-1 times 3, which is roughly 4n. So we can see that in this case, we're probably roughly exactly 1/4. We select this vertex, which we need. Okay, so at least for this reduction rule in particular, in this specific reduction rule cannot be improved in the sense that we cannot beat 1/4, which leads to a forward decay algorithm. But again, our goal is to do something very similar, and we want to kind of modify the reduction rule and get improvement here. We'll see this later on. Okay, so let's first discuss. Now let's discuss our approach. So at a high level, what we do is we want to split the problem into 2 cases. So we call a dense case where number of edges is much larger than the parameter k. So this is not the traditional notion of a dense graph where we want to compare n with n. Here we want to compare n with k. But you can think of a dense case as there's a lot of edges. In a sparse case, there's few edges. And in each case, we want to make an improvement. So in dense case, we want to modify the Becker sampling algorithm, and instead of sampling with instead of sampling each vertex proportional to the degree, we want to sample v with probability 3 minus 3. So this is valid because again, every vertex v has degree at least 3 after we perform the initial reduction rules. The graph is 3 regular, then this is kind of a corner case, in which case let's just sample v uniformly randomly. But we don't have to worry. Don't worry about that case. It's not a big deal. The point is, by weighting v by degree minus 3 instead of degree, we can obtain an improvement in the case m is much larger than k. Okay. And just some intuition on why this might lead to improvement. Well, in order to improve the success probability, it must improve the success probability in the hard case for the Becker algorithm, which is just this path graph with a single vertex. But in this case, since all the path vertices have degree 3, once you subtract 3 from the weighting, these have weight 0, whereas the single vertex in the feedback vertex set still has degree roughly n. So in this case, we actually succeed with probability 1. So this example is no longer a bad example for the sampling algorithm. So this at least some intuition on why weighting by degree minus 3 might help us. It kind of like kills off all of the degree exactly 3 vertices not part of the feedback vertex set, which are the ones we don't want to select. So a more concrete lemma we prove is that if m is much larger than, let's say, 100k, then this reduction actually leads to probably 1 over 2.99. Now the significance of this number is just it's a number less than 1/3, which is good because it gives us a running time of 2.99 to the k. Once we because again this can only happen k times, and our success probably becomes 1 over 2.99 to the k. And we can just repeat this this many times to get this algorithm succeeding with high probability. So again, the threshold we want to beat is set probably less than 1/3, strictly less than 1/3, so that we can kind of modify this to get a faster than 3 decay algorithm. So the other case is the sparse case where m is less than a constant times k. In this case, our key observation is actually, so it's well known again that the graph any graph with a Feedback vertex of size k has Treewidth at most k plus 1. But actually in this case, if the graph is sparse enough, then actually we can show that the graph has Treewidth strictly bound away from k. So it has Treewidth 1 minus epsilon times k. And that's good for us because we can then run the 3 to the Treewidth algorithm, and this will take time 3 to the something strictly smaller than k, which is again some 3 minus epsilon times to the power of k. And moreover, we can find such a tree decomposition, and we'll see this later on. Any questions so far? So this is our high-level approach on this is our high-level algorithm. We'll go over both steps in this talk, and they'll be mostly self-contained, with the exception of I will not define Treewidth, but if you're familiar with it, it should be pretty clear that that everything seems to work out. So any questions so far? Okay, so let's first go over this dense case where m is much larger than k. And to do so, let's first prove to see why we get an improvement much better than 1/4. Let's first prove the Becker's algorithm, where we sample it probably proportional to its degree, not degree minus 3. And we'll kind of modify this proof later on to see why by sampling with degree minus 3 and having this assumption, we can get a much higher success probability. Okay, so let's first prove the Becker's lemma. And note that to prove this, sampling v with probably proportional to its degree is equivalent to sampling random edge in the graph, and then given this random edge, sample random endpoint. So these two processes are equivalent. The latter one is nicer to analyze for the proof, so we'll kind of stick with this. So in the proof, suppose G has a size k FES. Let's break up this graph into the FES and the rest of the graph. So what we know is, again, we're assuming that G has min degree 3. So in particular, all the vertices in G minus FES have min degree 3. Moreover, by definition of FES, G minus FES, the induced subgraph, is acyclic. So in an acyclic graph, the average degree is at most 2. So here we see there's a gap between this 2 and 3. And this gap helps us because, well, since G minus the FES has degree at least 2, and the entire graph G has degree at least 3, we must add at least one vertex. We must add at least one edge per vertex once we add back in the FES. So in other words, every vertex in G minus FES must have on average one edge to the Feedback vertex set. Now, so that's a lot of edges. That's good for us because again, we're sampling a random edge. So if we sample one of these blue edges, then maybe with some good we'll probably 1/2 will sample the Feedback vertex set. So that's good. So the more blue edges is good for us. How many blue edges do we actually have? Well, so again, we want to compare these blue edges to black edges. These black edges are bad because if we sample a black edge, then both endpoints are not in the FES. So we kind of want to bound the number of blue edges versus number of black edges. But we can do that because the graph G minus FES is acyclic. So on average, there's almost one edge, black edge, per vertex in this graph because it's acyclic. But we also know that there's at least one edge for each vertex in G minus FES that is blue. So that means that there's at least as many blue edges as black edges. So we sample a blue edge with probably at least 1/2. And given that event, we sample the vertex in the FES with probably at least 1/2. So that's 1/4 overall. So that's a very quick, hopefully intuitive proof of why this simple sampling degree gives us a success probably 1/4. And again, it's crucially using the fact that the min degree is at least 3, where 3 is bounded away from this average degree 2 in the acyclic graph. So now at this point, we want to kind of like modify our proof. What changes in our proof once we sample with probability degree minus 3? So what changes is now at this point, let's go back to this. Let's go back to imagining sampling V with probability proportional to its degree. So imagine that every vertex has a weight equal to its degree. Now, what degree minus 3 sampling is doing for us is essentially it's weighting the total weight inside the FES by an additive minus 3k. So we kind of, the total weight inside the FES kind of drops by 3k, whereas the total weight of G minus FES drops by 3 times the number of vertices in here. Now, intuitively, this is very good for us if the size of the size of G minus FES is much bigger than the size of FES, because in that case, we decrease the total weight inside G minus FES decreases much faster than the total weight inside FES, which kind of weights us in a good way, because we will be selecting vertex in FES with higher probability. So that's intuitively why this kind of weighting might help us. More formally, we kind of divide the problem into two cases. First case is m is much larger than n. The second case is n is much larger than k. Now, note that if m is much larger than 100k, then one of these cases must happen, because if both cases were false, then we get m is at most 10n is at most 100k. So it suffices to divide the problem into these two cases. So first case is, imagine that the graph is actually dense, like the average degree, the number of edges at least 10 times the number of vertices. So in this case, we want to kind of modify our proof of Becker et al. And see why this will give us a much higher success probability. So for simplicity, for this case, let's ignore the -3 in our sampling. So suppose if the graph is dense, let's just repeat Becker et al. And we'll show that this actually gives us a good success probability. So why is that? Well, now if m is at least 10n, then the average degree is at least 10. Hold on. I guess actually it's like 20, but it's at least 10 in particular. But again, there's that the degree in the G minus FES is at most 2 again, because the graph is the remaining graph is acyclic. So in this case, in order to go from 2 to back to 10, we must add at least 8 edges per vertex in G minus FES on average. And here, that means that for every black edge, there are 8 blue edges on average. So that means that our probability sampling of blue edge is it's much higher now. It's like 8, 9. And this will boost our success probability to like close to 1/2, because this is close to 1. So in particular, the success probability is at least like 1/2.99. So in this case, we don't even need the degree minus 3 sampling. And turns out the sampling with degree minus 3 can only help us, but we won't show that. So in this talk, just assume that in this case, the algorithm can even just repeat the Becker et al. Algorithm. So now in the second case, suppose that n is much larger than 10k. In this case, we have many vertices. So in this case, this is also the case of our hard example from before, where we have a path graph and a single vertex. So in this case, we do need this degree minus 3 sampling, and let's see why it helps us. So in this case, the point is the new intuition from before, which is we're subtracting 3k from the total weight inside FES, but we're subtracting 3 times G minus FES, the number of vertices in here, from G minus FES in our sampling. And if n is much larger than 10k, then then G minus FBS is like at least 9K. So we're kind of subtracting with a ratio of -1 to -9. Now recall that initially the ratio is like 1 to 4, because in the hard case of Becker, the worst we can do is the total ratio between weight inside FES and weight outside FES is 1 to 4. But now we're subtracting stuff at a 1 to 9 ratio. So that really helps us. That boosts the success probability of sampling something inside the FES. And so why is it significant? Well, so imagine the graph is sparse in this case. So the definitely a question of weight. And if a constant fraction of total weight gets subtracted based on such a high ratio, then we can imagine that this probably 1/4 gets boosted up significantly higher. In this case, it does, and it can be boosted up beyond 1/3. So yeah, those are two cases, and I kind of sketch out a proof of why both cases lead to a high success probability. And again, if M is at least 100K, then either case must hold. So the success probability becomes based on which case it is, regardless of which case it is, the success probability is bound away from 1/3. So any questions on this slide? Okay. So that concludes it for the dense case. So now we'll proceed for the sparse case, but before that, we'll first go over this trick of iterative compression, which is popular in parameterized complexity, which kind of, as Pankaj showed before, mentioned before, it kind of gives us this feedback vertex of size k+1 for free, and we'll need this later on in our sparse case of the algorithm. So again, original problem is just given a graph G and a parameter K, find a feedback vertex of size K or determine that none exists. What iterative compression gives us is it gives us the following potentially easier problem, but can be reduced from the original problem, which is given a graph G and a feedback vertex of size K+1, determine whether there's a feedback vertex of size K or determine none exists. So why is it called a compression? Because we're compressing a FES of size K+1 to an FES of size K. Whereas before we were just looking for this FES of size K given no prior information, aside from just the graph. So this is kind of, and one might hope that like this initial information of a near optimal FES, like K+1 versus K, which is near optimal, might help us. And in this case, it does. Okay, so you can more concisely, you can think of it as we're just given as input a size K+1 FES for free. So a quick sketch of why, to those who have not seen iterative compression, a quick sketch of how this is done is basically we kind of add the vertices. So imagine ordering the vertices from V1 to Vn. And the idea is basically we just want to add vertices one by one and apply this compression. And then on each step, we compress a currently known FES of size K+1 to a new FES of size K. So we kind of do this n times, once for each new vertex that we add to the graph. So set the once we add vi+1 to the graph, now we're interested in the graph induced on the first i+1 vertices. Well, if Si is a via vertex set of the first I vertices, then by just trivially adding the new vertex vi+1 to the graph, this will become an FES of the new graph, and the size increases by 1. So suppose we know inductively that we have an FES of size K in the graph on the first I vertices, then we automatically obtain for free a vertex of size K+1 for the first I+1 vertices. And at this point, we can just compress, use the algorithm given this FES of size K+1, and compress it back down into. So we can compress it down back into a v vertex of size k. So more formally, what that means is we're solving the graph on the induced graph on the first I plus 1 vertices, together with the phi vertex of size k plus 1, and we get some FES si plus 1 of size k. But now back down to k on the first I plus 1 vertices. We kind of just repeat this. Every time we add a vertex, we compress and repeat this. And this shows that we can essentially reduce the problem to the case where we're given an FES of size k plus 1 for free. So this k plus 1 is not very significant. This could have been k plus any constant. But in terms of we can get k plus 1, so and what I mean is any k plus constant would have sufficed for us, but since k plus 1 is doable, we'll just assume k plus 1 for the rest of the talk. So essentially, this slide is just saying that we can assume that we're given FES size k plus 1 for free. So why does it help us? So for this, this will be the most like technically advanced slide for the talk. We'll essentially go over the sparse case in a single slide. So this will be the slide will be kind of dense, but hopefully it's not too complicated. I don't think it's too complicated. Right. So yeah. So our key element for the sparse case is that given the graph with m is at most 100k, and given FES size k plus 1, we want to construct a tree decomposition of the graph of width like bounded away from k. So 1 minus epsilon times k. So the way we're going to do is we're going to construct the following kind of structure. We want to kind of partition the graph into this following structure, which automatically implies a tree decomposition of size bounded away from k. So that part, the second part, I will not show because I will not formally define tree width. But it should be clear that since acyclic graphs have tree width 1, and right, it should be clear. It should be clear how this leads to a tree width bounded away from k. So what does the structure look like? So we have a separator that separates the graph into two pieces. The separator has size. So think of epsilon as some small constant bounded away from 1. The separator has size 1 minus 2 epsilon times k, and it separates the left and the right. Think of the left and the right as like two like roughly balanced pieces of the graph. So now we want to claim that this graph implies a tree decomposition of size, a tree decomposition of bounded away from k. Oh, again, so each side has a few vertices of size epsilon times k. And if we delete those vertices, then we get a forest. So it's essentially each side of the graph has a phi vertex set of size epsilon times k. And the middle has size 1 minus 2 epsilon times k. And this 2 is significant. Like we want to compare this 2 epsilon versus this epsilon here. And the fact that they're bounded away from each other gives us this boost of 1 minus epsilon times k for the tree width. So I want to claim that this graph has tree width almost 1 minus epsilon times k. Again, if you're not familiar with tree width, you can just skip like the next 1 minute or 2 of the talk, where I just kind of sketch out why this structure is what we need. So here's like the very quick proof of why this is true. So the tree width of any forest is 1. Now, so given a forest, given a graph of a small tree width, adding a vertex, an additional vertex to the graph, can increase the tree width by almost 1. So in this case, the tree width of the forest plus these epsilon k vertices can be at most 1 plus epsilon k. And this is true for the other side as well. Now, these two graphs are disjoint without the separator. So since each graph has tree width at most 1 plus epsilon k, unioning the two graphs, disjoint union of two graphs with no edges in between, cannot increase the tree width. You just get the max of the two tree widths. Now, finally, we want to add the separated vertices. Now, there are 1 minus 2 epsilon times k separated vertices. So by adding them, we get an extra 1 minus 2 epsilon. Now here's where this 2 epsilon benefits us versus this epsilon. And we get, it balances out to get a 1 minus epsilon times k at the end. So this is why, so for the rest of the talk, we'll like ignore Treewidth, and we'll just focus on establishing this structure. So so why do we get the structure? So how do we get the structure? So first, again, we're given an FES size k plus 1. And when we remove these vertices, we get a forest. So first step is we want to take this forest and kind of break it up into smaller pieces. So we want to remove some little o of k. So think of this as negligible set of vertices from the forest such that every remaining component of the forest is small. We'll define small later on. This small will be useful for some like concentration bounds we'll need later on. So for now, let's ignore what small means. And so the vertices that we remove, we'll just greedily add them to the separator. But this has little o of k vertices. So think of this as like k over log k or something. So it doesn't really affect the separator size because epsilon is a constant. So now that the forest part of the graph is broken up into smaller pieces, what we want to do is we want to, for each component, for each small piece of the forest, we want to color it red or blue with probably 1/2. So imagine every component independently is colored red or blue with probably 1/2. Now, how do we construct our 2 forest pieces? Would we just move the red components on one side and the blue components on the other side? And again, each of these is a forest and they're a disjoint union, so each of these is a forest. So now what happens to the vertices in the FES? Right, so here's another step we need to do, because we want to color the edges between the FES, red or blue is probably 1/2 each. But you can also assume that, like, suppose that the phi vertex is an independent set. This might make things simpler, but in full generality, we will kind of color the vertices between the FES as well. So again, each edge between 2 vertices in the FES get colored red or blue probably 1/2. Okay. So now, now what we do, how do we get these size epsilon k sets from left and right? Well, suppose a vertex in the FES has only blue edges. So suppose a vertex in the FES has only edges adjacent to blue vertices. So in other words, this vertex here, the edge in the FES was sampled. Can you see the cursor, by the way?
Yes.
Okay, cool. So in particular, this vertex here, it has the edge adjacent, the edge incident, this edge is colored blue, and its neighbors to the forest components are all colored blue. So this edge, this vertex has only edges to blue components. So in this case, we add this vertex to the blue side. And similarly, for the vertices that only have red edges, we add it to the red side. So this is what it looks like right now. All the other vertices where there's a vertex to the blue component and a vertex to the red component, these we won't add them yet. But these will eventually go under the separator. Okay. Yeah, finally, all the remaining vertices we just add to the separator. So this is our structure. And essentially, we want to show that there are enough vertices here and here, at least epsilon k, and this gives us what we want, because then the remainder has, if we add at least epsilon times k to each side, the remainder has size at most 1 minus 2 epsilon times k. So why is this true? Why is there like a good amount of vertices in the FES whose neighbors are all red? Well, so for each vertex, imagine, so for each vertex, consider its degree. So the total number of components, the red components here, that are adjacent, the total number of pieces in the forest that are adjacent to it is at most its degree. Let's ignore, for example, simply let's ignore the edges between the vertices and the FES. So the point is, and each of these pieces is sampled red with probability at least 1/2. It's probably 1/2. So the probability that all the incident edges are red is sampled probably 1/2 to the degree. At least that. It could be more. It could be less if, like, for example, all the edges belong in the same component. Then they're like positively correlated. So that's good for us. So what is the expected number of such vertices? Well, it will be just a sum of the 2 minus degree. And since 2 to the minus x is concave, it's convex, by Jensen's inequality, this gives us the size of the FES times 2 to the minus average degree. And the size of the FES is k. And here, now we're using the fact that the average degree, sorry, the size of the FES is k plus 1. Now here we're using the fact that the average degree, so this is the average degree of the vertices inside the FES. Well, that's at most 2m, the total number of vertices in the graph total, divided by k plus 1, which is at most 200. So this is a constant. So here, this gives us like a constant times k, where we'll just be setting this epsilon to be this small, very small constant. Okay. Now, again, what we want is, so this means that on average, we do well here. On average, we do well on the other side as well, because it's symmetric. But of course, what we want is we want both sides to do well. We want both sides to be at least epsilon times k. And this is where we need some concentration. So what we do is we want to make sure that each of these pieces is small in some definition of small, such that we can apply these concentration inequalities. Like with high probability, we get at least epsilon k here, and with high probability, we get at least epsilon k here. So that with some positive probability, we get it for both sides. So what is this definition that we need? Well, so I'll just go over this very briefly, but essentially, what would be bad for our case is if a single component has neighbors to all of the FES. If a single component has neighbors everywhere, then that's bad because that essentially gives us like no concentration. That gives like the opposite. Whatever color this is, everything here will be on the same side. So essentially, we kind of want to break up the graph so that every piece has a small number of total edges to the FES. We want to kind of break it evenly. Where by even, I mean, how many edges does the component have to the FES? That's the important metric. And if we do that, then it turns out we can establish these concentration inequalities and get that with positive probability both sides happen. So any question on this slide? So that's all there is for this slide. That's all there is for a sparse case. So we do this simple random sampling trick, and along with the fact that the average degree is small in the FES, that gives us our improvement. Okay. So to conclude, to speed up the algorithm from like 3 minus epsilon times k to the k to 2.7 to the k, we do some more work. First of all, we tighten the degree minus 3 analysis. So far, the analysis we saw was not tight. We had these very large constants. But if we tighten the analysis, then we can get some I think 2.8 to the k algorithm. Now to improve this further down to 2.7 to the k, what we do is we want to open the box of the Treewidth algorithm by Cygan and al. And how we do that is, turns out that Cygan and al, the algorithm behind their paper is called Cut&Count. So what they do is they actually solve a counting problem on cuts of the graph. And counting is like a inherently arithmetic kind of problem. And this Cut&Count algorithm has some special arithmetic structure that allows it to be sped up with fast matrix multiplication. So it turns out if we apply fast matrix multiplication, then this actually gives an improvement. And why that is, like, it's very complicated and requires diving deep into the Cut&Count algorithm, but this gives an improvement. So finally, the open problems. The main message of this talk is conceptual. It's just the fact that the 3 to the k barrier can be broken after like 9 or so years. And one still open question is, can we get a factor deterministic algorithm? Like, can we match the previous 3 to the k randomized algorithm with the deterministic one? This specific algorithm is inherently randomized because the Becker algorithm is also randomized. So there doesn't seem to be much hope in de-randomizing this algorithm. But at least can we match 3 to the k? Can we de-randomize this Cut&Count algorithm due to Cygan and all? That would be very nice to see. Another question is, can we perhaps improve this 2.7 to the k further and get maybe down to 2 to the k? I think this will likely require some new ideas, some new cleaner ideas, in the sense that our result was kind of just like fighting for any small improvement on 3. I think we got lucky that we got such a big improvement below 3, but it could have as likely been like 2.999 to the k that we got. But I think getting all the way down to 2 to the k will require some new ideas that will potentially be useful for like other problems in parameterized complexity. And finally, what about like a lower bound? Turns out this FES problem is special in the sense that there's no like constant to the k lower bound known, assuming STPH. So showing this will be also very, very exciting. So yeah, that concludes my talk.
Thank you very much. So, please ask questions.
Oh, directed FES is also a very classical problem. I think it was a major open problem. So correct me if I'm wrong, because I'm not super familiar with directed FES, but it was a major open problem until like the late 2000s, where it was shown to be it was first shown to be FET in late 2000s, which is much later than like many of the open problems. For example, undirected FES was shown in like 1992. So this used to be a major open problem, and it was shown to be FET in late 2000s. Currently, no single exponential time is known for this problem. So I think the current one's like roughly like there's like this k factorial term. So it's like k to the k. So it's a I think I would consider a major open problem to get a single exponential for directed FES. Again, these techniques are highly used to find the graph is undirected. So, for example, like a complete tournament, like a complete like a graph can be complete and also acyclic. So the notion of degree is kind of like less well defined in the directed case. So it's a lot harder. Oh, so space dependency. So it can be made polynomial space by opening up this Treewidth algorithm. So I think naively you get exponential space, but if you open up this Treewidth algorithm, you get polynomial space, and the space is roughly like 2.8 to the k. This is like when you just tighten the analysis, we do not use this fast matrix multiplication. Now, if you want to use fast matrix multiplication, then you do have to suffer exponential space, because these matrices that you multiply are size constant to the k. So these are big matrices, and you need to store them in space in order to multiply them. So so the message is 2.7 to the k requires exponential space, but some 2.8 to the k can be done polynomially in polynomial space by opening up this 3 to Treewidth algorithm.
I'd also like to ask a question.
Sure.
About the hard examples for this Becker sampling routine.
Mm-hmm.
So you showed a couple of the standard reduction rules, and there's one more fancy reduction rule that you didn't show. So it's called the flower rule. A k flower in a graph for one particular center vertex is a set of k cycles which are disjoint except that they all share v. And in polynomial time, you can compute a maximum cardinality flower.
Oh, that's
And
interesting. Yeah.
If you look at your example, then you could already tell if your rotate is one and cycles as possible intersecting only your top vertex, then that computation would already have told you that there are more than, say, 3 cycles intersecting only at V. So if there's going to be a size 1 feedback vertex set, it has to pick that top vertex anyway. So my question is it conceivable that if you do this deterministic, more fancy flower-based reduction rule, then afterwards this, say, Becker sampling would be better than 1/4?
Yeah, actually, that's actually potentially true. Like, I don't see a counterexample yet, because if we let's go back to so this path lower bound, this path plus single vertex kind of lower bound, it relies on the fact that the path is acyclic, is a tree. First of all, this graph is a tree, and also it has max degree at most 3. I think like once the vertices have degree more than 3, then you get a benefit. But on the other hand, if the graph is a tree and it has max degree almost 3, then it seems like you can, and every single vertex is connected to the root. Oh, actually, hold on. Yeah, it seems like if the tree has low degree, and everything's connected to the root, then it seems like you can indeed find these like K flowers. So that is possible. I don't see a counterexample yet.
Okay, thanks.
So perhaps like you want like, if you're trying to find a counterexample, maybe like the graph should have many vertices degree 3, and also many leaves to compensate for the average degree to be 2. The degree 3 vertices will have no edge to the vertex because it has already degree 3. The leaves will have two each. Oh, but the leaf has yeah, I guess 2 parallel edges will make a flower as well, right?
Yes.
Yeah. So yeah, that's actually very possible. That might actually be true. Yeah. Whether it goes from 4 to the K down to less than 3 to the K, because there's still a gap that you need to like improve. You still have to go from 4 to 3. So it's less clear that the gap will be significant enough that you get an improvement. At least the naive Becker-Intell approach. Any other questions? Oh, sorry. So more than 2 colors in the last step. Right. So currently in this analysis, if you use more than 2 colors, there's no benefit. Turns out, essentially like, okay, can I annotate here? Not sure if I can annotate. But the point is, suppose you kind of naively just use like, let's say 3 colors. So what's going to happen is you're going to have like 3 pieces and a separator that connects everywhere. But the point is, the probability of belonging to one piece becomes 3 to the power of minus degree, which is worse than 2 to the minus degree. So naively, it seems like there will be no benefit in choosing 3 colors. But it turns out we actually use 3 colors if we want to apply fast emission multiplication. So it turns out 3 to the degree might be smaller, but the benefit we get from fast matrix multiplication in the final 2.7K algorithm, actually the benefit in using fast matrix multiplication versus like naive n cube multiplication gives us actually enough benefit that it's actually preferred to use 3 colors. And 3 seems to be natural for matrix multiplication because actually is it clear? Yeah, actually it's not so clear, but turns out yeah, so the 2.7K algorithm actually uses 3 colors, and that's where by using fast matrix multiplication it actually helps. Upper bound Treewidth further. So I think, at least for this analysis, the best you can get is the expectation. So I think the lower bound here is just like the expectation is too large to get any improvement, and in order to improve upon this construction, you want to reduce expectation. And so far, the only thing we know is the only thing I know is just do this random sampling and get this like 2 to the minus degree, which is it's not so satisfying because that really means that the degree must be really small to make this any significant improvement. But I don't know of any better way to do this other than just like random sampling with polynomial path. Sped up version of CNP. Okay, yeah, it gets a little complicated. So imagine, so to speed up Cygan AL with matrix multiplication. So again, first of all, we're sampling with 3 colors instead of 2. So we have 3 colors. Now we want to divide these separate vertices based on which of the pieces it kind of intersects. So some of the separate pieces might only have edges to 2 of the components, and this will be important for us. So so imagine I have 3 pieces. Because like that'll be very useful. Yeah, I don't see a way to maybe I'll come on. Can you see the paint? Okay. So let's suppose we use 3 colors. Now we want to divide the remaining vertices, the vertices in FPS, into whether it's completely inside here, whether it has only neighbors to 1 component, or whether it has neighbors to 2 components, or whether it has neighbors to all 3 components. So here we want to distinguish between 2 components versus 3 components because actually turns out this is actually what matrix multiplication can do for us. So now I think the point is we first want to solve like these pieces. And this kind of gives us like a matrix between these dynamic programming states where again, so I'm like really going deep into like the Cygan algorithm. So so like this kind of assumes that you know the algorithm pretty well. But the point is for every dynamic programming state, let's say for every dynamic programming state where we kind of divided the state into like the division, are they I think this maybe 3 colors, but the point is for every dynamic programming state, we kind of solve this problem, this subproblem for each of the 3 pairs, like each of the 3 pairs here. And the point is we can like kind of construct a matrix based on like dynamic programming state here versus the state here. So like this will be our entry at least for this state. And now the point is we need to kind of like now we kind of want to extend this to like all 3 states, right? All 3 states. And here's where matrix multiplication helps because we're kind of multiplying kind of the number of ways to do it here times the number of ways to do it here times the number of ways to do it here. We're kind of multiplying these 3 matrices together. one for, let's say this is 1. This is 1. And the 2 would be like here. And 3 would be here. So this is where we're using matrix multiplication. Yeah, I don't think I can go into too much detail right now. It's fairly complicated.
Okay, maybe we should stop here. So
Okay.
Thank you once again, Jason, and see you, most of you, next Thursday. Yeah. Thank you, and bye.
Bye.